let's talk about the simple mechanisms that are observed in organic chemistry reactions. And we'll start by examining Sn2 reactions, or substitution, nucleophilic, and bimolecular. That's what the Sn2 stands for. There's also Sn1, which would be substitution nucleophilic unimolecular. So here we have kind of an acid-base reaction, and this is why we're starting with it. But we have a full negative charge on this hydroxide. And then if we look over here, we've got a partial negative charge on the chloride, and therefore we'll have a partial positive charge on this carbon. That will attract the negative charge on the hydroxide, and we could substitute it for the chloride. So what happens is we'll see this come over and attack the carbon, and then those electrons will then move over to the chloride. And what we'll get is methanol and a chloride. So let's draw that. And there we have the chloride with the negative charge on it now. Similarly, we can have reactions that are Sn2 with a species that does not have a negative charge, but it will have an area of electron density, such as this ammonia molecule right here. Now we have this large sulfonyl group, and that will leave when this ammonia comes in. So, like up here, we have a carbon that has a partial positive charge, and this one will have a partial negative charge here on the oxygen. So, if we draw the mechanism for this, we'll have these electrons coming down here and attacking this carbon, and then those electrons will then associate with the oxygen. And what we'll have is this. Now we'll have a positive charge on that nitrogen still, and then the sulfonyl group will have a negative charge associated with it. This negative charge is particularly stable because of the resonance that exists for this molecule. Feel free to draw the resonance structures. It's a good exercise. I'll skip that for this video. But that brings up an important point. We really should talk about what a nucleophile is and what a leaving group is. Well, over here we've had two examples of nucleophiles, and we've had two different leaving groups. We have the chloride, or in general halogens except for fluoride will make good leaving groups, and this sulfonyl group, which makes a good leaving group because it has charge stability. This is an electronegative atom, so it has good charge stability too. All right, what is a nucleophile? Well, a nucleophile is a species that has a lot of electron density and would like to be attracted to the nucleus. And as you know, the nucleus has a positive charge, and so that's where the name nucleophile came from. We also have things called electrophiles, which would attract electrons, and those are positively charged, whereas nucleophiles, they have either a full or a partial negative charge. So They can have either a full or partial negative charge or an available lone pair. And these will typically make up what are nucleophiles. And then let's also talk about leaving groups. In order for this mechanism to occur nicely, we do have to have some group that is capable of leaving and providing the space that will happen. And this has to happen all simultaneously. So this will come in and this chloride will be leaving. So what we like in a leaving group is that they're able to stabilize the negative charge that gets left on it. So and the typical examples of good leaving groups are conjugates of strong acids. So that's another reason why fluorine is not considered. But realistically, one of the main reasons is it forms such a strong bond with carbon, it just is hard to break, and that's not going to make a very good leaving group. So conjugates of strong acids. Make good leaving groups. So chloride, bromide, iodide, those are all conjugates of strong acids, HCl, HBr, HI. So those make excellent leaving groups. Also, if they're resonance stabilized, like this methyl sulfonyl group, this negative charge is resonance stabilized across the molecule. And water or alcohols make excellent leaving groups as well because they're conjugates of strong acids. So this is just a little bit about nucleophilic substitution by molecular reactions. Remember, these steps occur simultaneously, so we'll have our nucleophile will come in and attack, our leaving group will then leave, and that will all happen simultaneously. And you'll notice there's two steps, and it's very similar to an acid-base reaction. And in fact, some chemists would qualify these as bases. Well, certainly hydroxide and ammonia are qualified as a base, but they would consider nucleophiles more generally to be another definition for a base. So if that helps you identify nucleophiles, that's a good way to think about them.